Hi, in this video, we are going to start a new series. This is on vectors and 3D geometry. So this is a super important chapter for the point of view of JEE Mains and JEE Advanced. And there are a lot of questions that you will see in Mains and Advanced from these topics. It's also a very easy chapter if you know your theory. So if you pay attention to this series of videos, you will make sure that vector and 3D is no longer a problem for you. So let's begin with vectors today. So in this video, we are going to start with basic properties of vectors, addition of vectors, coplanar vectors, vector in a plane, and things like that. So let's discuss what a vector is. So basically, the first thing that you need to know about a vector is a basic idea from physics that it is a quantity that has both magnitude and direction. Magnitude and direction. And usually we represent vectors with line segments showing the direction. So if it is a A to B line segment, then this is known as your AB vector, right? And the point here is that this AB vector is represented by the length AB, the length of the line segment, AB is the magnitude of the vector, magnitude of the vector. It is also sometimes written as mod AB. So mod AB is basically the magnitude. And the direction of AB can be specified in multiple ways. The direction of AB vector can be specified in multiple ways. You can either show it as a particular angle with the x-axis. Let's say here we are saying that it is making theta angle with the positive x-axis. Or you could also write the direction in terms of its components. So I can think of this vector in the plane and think of it as I cap and j cap components, and maybe it is x I cap and y j cap, right? So you can also write the vector AB as x I cap plus y j cap, right? So here again, tan theta is y by x here, right? So a vector has magnitude and direction, and you would say that we can represent that vector either with a straight line from an initial point to a final point, or you can write it in terms of components, right? Some basic things that you need to know are what is a unit vector, for example. What is a unit vector? It's a vector of magnitude 1, vector of length or magnitude 1 unit, right? It can be in any direction, but it has to have length or magnitude to 1, right? That is a unit vector. What is a zero vector? A zero vector is again a vector of length 0. Length 0. So basically, if you try to write a zero vector, it has to have 0 in all the three components, x, y, and z, right? Also, what is equality of vectors? Equality of two vectors. So we say that vector A is same as vector B if and only if all the three components of A and B are same. A and B are same. What do I mean by that? So A could be having components AX I cap, AY J cap, and AZ K cap. And B could be having components BX I cap plus BY J cap plus BZ K cap. Now, if the two vectors are equal, we can say AX is equal to BX, AY is equal to BY, and AZ is equal to BZ. If the two vectors are equal, right? This also means that mod of A is equal to mod of B, right? Because the magnitude of the A vector, if it is written in terms of components, the magnitude is simply root over AX square plus AY square plus AZ square. And that has to be equal to root over bx square plus by square plus bz square, right? So equality of two vectors is a very important idea that you need to understand. Another term that you might have seen in physics is position vector. What is the position vector of a point? So let's say you have a point in space somewhere here P. The position vector is the vector joining the point P from the origin to that point. If you draw a vector, that vector becomes the position vector or R, right? So if the point P has coordinates x, y, z, and origin is obviously 0, 0, 0, your position vector of P is becoming x I cap plus y j cap plus z k cap. So position vector concept is very important in physics, and you must have already understood that. So I'm just revising these basic ideas right now. Now, the first major thing that we'll talk about is vector addition. Vector addition. So think about two vectors. If A and B are two vectors, then then we can say that there exist 3 points, capital A, capital B, and capital C in space, such that A vector is denoted by the segment AB, B vector is denoted by the segment BC, and then A plus B is defined as AB plus BC, and that will be equal to the AC segment. So let's say we have this figure. This is my situation. A vector is this, point is A, this is B, and this is C, let's say. And B vector is this. This is my A vector, this is my B vector. This becomes your C vector. C vector is equal to A plus B. So your segment AB was representing the A vector, segment BC was representing the B vector, and segment AC is the resultant of AB plus BC, which is basically A plus B vector, which is called C vector here. And this is basically the triangle rule of vector addition. What is this triangle rule? So anytime I have two vectors and I want to add them, right? So this is X vector and this is Y vector. What I can do is I can lift the X vector and put it like this here. When I translate the X vector to this point, what I'm doing is keeping the magnitude same, keeping the magnitude of X vector same, and moving it parallel to itself, basically without changing its orientation, without changing its direction. So because I have lifted X vector from here and placed it here, I have ensured that I have not changed the magnitude as well as the direction. Then instead of adding the two vectors from this point, I'm going to now think of it like this. First you go in Y direction and then you go in X direction. So the resultant vector will be the third side. So if you have two vectors which are forming two sides of a triangle in such a way that the head of this vector, this is the head and this is the tail. The head of the first vector is meeting the tail of the second vector, right? Then you are going to be able to arrange them in such a way that they form two sides of a triangle, and therefore you can find the third side will be your addition vector. So your z vector would be the third side, and that would be your x plus y. So that is the basic idea of triangle law of addition, right? I'm sure you already know this. I'm just saying it because we are going to cover the theory completely. So these basic things you should be aware of by now, right? The next point that I want to talk about is if A and B are any two vectors, then the addition of two vectors is commutative. So A plus B will be equal to B plus A. So addition is commutative. This is known as the commutative property, right? So that is an obvious statement. Whether you go like this and do A plus B and that is C, or whether you do it in a different way. So you have B here and you can lift A and join it somewhere here like this. Lift A parallel. This is your A and this is your B. This is going to be your C, and this C vector is going to be parallel to the C vector you got from here, and it also has the same direction. It has same magnitude and same direction. The order of addition doesn't matter, right? The next property is the associative property, which is again very obvious. If A, B, C are any three vectors, then A plus B plus C is the same as A plus B plus C, right? So we can prove this also easily. Let's say A vector was my AB vector and B vector was my BC vector. And let's say C vector was CD vector. Then what is A plus B plus C? That is basically AB vector plus BC vector plus CD vector, and that is equal to AC vector plus CD vector, because AB plus BC will be AC. And now AC plus CD is clearly AD vector, right? However, this AD vector can also be written as AB plus BD vector, right? And now we can keep the AB as it is and split the BD as BC plus CD, and therefore now you're getting it as A plus B plus C. So this is the proof. I hope you understand each step. We are writing, this is our initial assumption. A vector is AB vector, B vector is BC vector, and C vector is CD vector. And from there we have proved that the order of addition doesn't matter. And that is the associative property of vectors, right? The next idea is if A is any vector, A is any vector, then if you add the 0 vector to A, it will be the same as 0 plus A vector, it will be the same as A vector. So 0 vector is the additive identity. By additive identity, I mean if you add the additive identity to any vector, it remains the same, right? Okay. Now, another point that is super important here is if A is any vector, then there is an additive inverse. Then there exists an additive inverse for A vector. What is an additive inverse? Basically, what I'm saying is A plus B will be equal to 0 vector. So we can always find a B vector, find a B vector such that A plus B is equal to 0 vector, right? So basically this B vector is going to be minus of A vector. 0 minus A vector will be minus of A vector. And this vector is the additive inverse of A. Basically, this vector, if A is like this, minus A is like this. It is in the opposite direction, but has the same magnitude as A, right? Okay. Now we come to some of the more important ideas. So this theorem is very important. It says if A and B are any two vectors, then first of all, mod of A plus B is less than equal to mod of A plus mod of B. This is the basic triangle inequality. We also have other versions of it. We can also say mod of A minus B is less than equal to mod of A plus mod of B. And third thing that we can say is mod of A minus B is going to be greater than equal to mod of A minus mod of B. So these three together are known as the triangle inequalities. So how do we prove these triangle inequalities? So if you look at any triangle like this, A, B, and C, let's say this is my A vector, and let's say this is my B vector, right? Now, obviously, A plus B is this side AC, right? A vector plus B vector is my AC. So what we are saying in the first one is AC mod is less than equal to AB plus BC. But that is a true fact because the sum of any two sides of a triangle always is bigger than the third side, right? Similarly, you can also prove the second one. So you have to remember here that these modulus represents the sides of the triangle, and this is the third side. So we are getting something like B is less than equal to A plus C, right? That comes from triangle inequality, and it's a basic property of any triangle. You can also prove the second one by using the first identity itself by saying A minus B mod is same as mod of A plus minus B, which will be less than equal to mod of A plus mod of minus B, which is equal to mod of A plus mod of B. So mod of minus B is same as mod of B. So this inequality follows directly from the first one, right? And now we can also show the third identity. So let's do the proof of the third identity. We have to show that mod of A minus B is greater than equal to mod of A minus mod of B, right? So what we can do here is we can write mod of A as mod of A minus B plus B. That is the same expression actually. We are adding and subtracting the same vector B, right? So we can say that this is less than equal to mod of A minus B plus mod of B. And that comes from the first property, the triangle inequality, right? So from here, we can easily deduce that mod of A minus mod of B is less than equal to mod of A minus B. So that is one version here. And also the other version also can be done. B vector mod is equal to B minus A plus A, and that is less than equal to mod of B minus A plus mod of A, which implies that mod of B minus mod of A is also less than equal to mod of B minus A, which is equal to mod of A minus B. Mod of B minus A is same as mod of A minus B because you can take a minus 1 common here. So we have proved this result and this result, and both of them together can be represented with a modulus sign because we don't know which one is bigger. This is bigger or this is bigger, mod A or mod B. So depending on that, we can say that mod of A minus B is greater than equal to the positive difference of the two mods, right? Now, think about it. These are triangle inequalities. When do you get an equality here? When do you get an equality, right? So if the vectors are in the same direction, if A and B are two vectors in the same direction, two vectors in the same direction, then you can say that mod of A plus B will be equal to mod A plus mod B. Usually you will say it is less than, but if if they are in the same direction, you are technically adding two vectors in the same direction. So the resultant vector will be the sum of the magnitudes of the individuals, right? Similarly, you can say that mod of A plus B is also equal to mod of A minus mod of B, but that is if they are in the opposite direction. If A and B are in the same direction, then their modulus gets added. If they are in the opposite direction, then their modulus has to be subtracted, which are pretty obvious statements, right? Okay. Then the next thing that we look at is the basic scalar multiplication or dot product of two vectors. Okay. So, okay, before dot product, we are doing scalar multiplication. And by scalar multiplication, I mean scalar multiplied with a vector. Multiplied with a vector. Okay. So let M be a scalar and a vector be a vector. Then the product of a scalar and a vector, the product M times a vector is defined as follows. What is the meaning of M times a vector? So if M is greater than 0, then M a vector is a vector of length M times mod of A in the same direction as A. In the same direction as A vector. Secondly, if M is less than 0, then the magnitude becomes minus M times mod of A is the length, and the direction is opposite to that of A, is opposite to A vector. And finally, if M is 0, then M A vector is basically the 0 vector, right? So this is your scalar multiplication, and what it means is that if you multiply a vector with a scalar, the magnitude of that vector will change, but the direction will remain unchanged. If M is a positive number, the final MA vector will have a magnitude of M times the magnitude of the initial A vector. If it was negative, the magnitude is still M times the magnitude of A vector, but the direction is opposite to the initial A vector, right? So some basic properties of scalar multiplication that you should know are, if M is a scalar, then and A is a vector, then we can say that minus M times A vector is equal to M times minus A vector and is equal to minus of M A vector. All of these three things are the same, which means that we can take the minus sign anywhere in this multiplication and it will be the same thing, right? Okay. Now we look at the idea of angle between two vectors. Angle between two vectors. Okay. So usually the angle between two vectors A and B is the angle AOB, where OA is your A vector and OB is your B vector, right? So the figure is looking like this. If A is this vector, OA is A vector, and OB is B vector, then this angle. Basically, you have to find the point of intersection of the line segments represented by the vectors, and the small angle here, the angle less than 180 degree between the two vectors when they have a common starting point becomes the angle between your two vectors, right? Now, if I represent the angle between two vectors with this notation, basically I'm saying this means angle between A and B, right? In that case, we can write down some properties of the angle between two vectors. So AB will be equal to BA. And what this means is the angle between two vectors A and B is the same as the ones between B and A. Similarly, the angle between A and B will be the same as the one between minus A and minus B, because minus A and minus B simply switches the direction of A and B. This is A, this is B. This is my angle that I was referring to. Minus A is like this and minus B is like this. So by vertically opposite angle, against it's the same angle between these two, right? Similarly, what we can also say is the angle between A and B vector will be, if that angle is theta, then what is the angle between A and minus B vector? That will be pi minus theta. Similarly, the angle between minus A and B vector would also be pi minus theta. So this is obvious from this figure. If the angle between A and B was theta, then the angle between minus B and A is this angle, which is pi minus theta, right? Also, one last thing here, the angle between m times A and n times B is the same as the angle between A and B. Because scalar multiplication only changes the magnitude of the vectors, it doesn't touch the direction. So this is the same direction, so it will have the same angle between the two of them, right? So those are some basic facts about angles between vectors. Now we start talking about collinear vectors. Collinear vectors. So two vectors are said to be parallel or collinear if they lie on a line, if they lie on a line or on parallel lines, or on parallel lines. So the vectors have to lie on the same line or they have to be on parallel lines. Then they are known as collinear vectors. So you can have A and B could have the same direction, or could have opposite directions. So technically you should realize that the angle between A and B should be 0 or 180 degrees, right? In that case, they are going to be parallel or anti-parallel, and therefore we can call them collinear, right? Now, think about it. The basic characterization of two collinear vectors. So if let A be a non-zero vector, A be a non-zero vector and B be any vector, then the condition for A vector and B vector to be collinear is A and B vector are collinear if and only if you can write B vector as equal to m times A vector for some scalar m. So if the two vectors are collinear, then they should be, you can write any one of them as a scalar multiple of the other vector, right? So if they are in the same direction, then that scalar multiple will be positive. And if they are in the opposite direction, then the scalar multiple would be negative, right? So for example, if A and B are in the same direction, we can say that the unit vector A will be equal to the unit vector B. The meaning of A and B having same direction is that their unit vectors will be equal to each other, right? Because unit vector, both of them have magnitude 1, but their and the direction are also same, right? So we can say B vector is equal to mod B into B unit vector. So that can be written as mod B into A unit vector. And therefore, that can be written as mod B into A vector divided by mod A vector, right? And this basically tells us that mod B over mod A times A unit vector, right? That is your mod B into mod A times not A unit vector times simply A vector. So we are able to show that B vector is equal to mod B by mod A times A vector. And M is your scalar mod B by mod A, right? So we are able to show that B vector is M times A vector. So that is the proof of this result, right? So again, repeating what is this condition, the condition for collinearity is that if two vectors are collinear, then one of them should be a scalar multiple of the other, right? And it's very important that you understand why this is happening. Now, what are the consequences of this result? So we can say two non-zero vectors A and B are collinear if and only if m times A plus n times B is equal to 0 vector for some scalars m and n not both 0. So both of the scalars m and n should not be 0, and there should be two scalars such that ma plus nb is equal to the 0 vector. Because if both are not 0, if m is not equal to 0, we can say that ma is equal to minus nb, and therefore we can write a as minus n by m into b. And if n is not equal to 0, then we can say nb is equal to minus ma, and we can write b as minus m by n into a. So both of them should not be 0 basically implies that one of them can be written in terms of the other multiplied by a scalar quantity. If both are 0, then we can't write this, and therefore then it will not be collinear, right? So this is a very important idea. Another consequence of this is the extension of this idea, which is saying let A, B, and C, let A, B, and C be the position vectors of points, be position vectors of points A, B, C, respectively. Then the points A, B, C, A, B, C are collinear if and only if MA plus NB plus P times C vector is 0 vector for some scalars M and P, for some scalars M, N, and P, such that M plus N plus P is equal to 0. Okay, so what we will do here is we will do the proof of this statement in order to understand this idea properly, because this type of thing can come in questions. Okay, so let's think about it. First part we'll prove is suppose A, B, and C are collinear points. Suppose they are collinear points. So that means they lie on the same straight line, A, B, and C, right? Then we can say that the vectors AB and the vectors AB and AC are collinear, which means that we can write AC as some alpha times AB for some scalar alpha, right? Now, what is AC vector? If my origin was somewhere here, this is OA, OB, OC are the position vectors of A, B, and C, right? Now think about it. This was my A vector, this was my B vector, this was my C vector. Because when I call position vectors, I mean vectors from the origin to these 3 points. Now think about it. AC vector is clearly C minus A in terms of the position vectors. And I'm getting C minus A is equal to alpha times. This is B minus A, right? So what I'm getting right now is this condition that C minus A is equal to alpha times B minus A. And this can be written as, bring everything to one side, you get A 1 minus alpha plus alpha B minus 1 into C is equal to 0 vector, right? Now notice here that this is my M, this is my N, and this is my P. And you can clearly see that M plus N plus P is equal to 0. Because 1 minus alpha plus alpha minus 1 is 0, right? So we have proved one part of it, that if the points A, B, C were collinear and OA, OB, OC or vectors A, B, and C are the position vectors of these points, then what we can say is that MA plus NB plus PC is 0, where M plus N plus P is 0 for some scalar quantities M and P. That is what we have shown so far, right? Now we'll prove the reverse of this statement. We'll say suppose MA plus NB plus PC is 0, where M and P are scalars which are not all zero, and M plus N plus P is equal to 0, right? Now, because M plus N plus P is 0, we can write M as minus N minus P, right? And I will try to put that back in the original condition. So I'll get minus N minus P A plus NB plus PC is equal to 0 vector. So now what I can write this as is N common B minus A. This is minus P times A and plus P times C. So there I can take a P common and I get a C minus A is equal to 0 vector, right? And what is B minus A? That is OB vector minus OA vector. And what is this? This is OC vector minus OA vector, right? Is equal to 0. So OB minus OA is going to be the AB vector. So this is AB vector by simple triangle rule of addition. And this is AC vector. Again by triangle rule, this is coming equal to 0 vector. And that means from the properties that we have seen, this implies that AB and AC are collinear vectors. And if they are collinear vectors, then that implies that A, B, C are collinear points. How can I say that? Because I can write AB vector as some scalar times. AB vector can be written as minus P by N AC vector, right? And here I am assuming that at least N is not equal to 0. Because you could have multiple of these M and P scalars to be 0 as long as not all of them are 0. All of them as 0 is not allowed, right? So we have proved both sides of the statement, and I hope you have understood what collinearity basically means, right? That is a very important idea that you should understand because you'll come across it in problems. Okay. The next topic that we'll talk about here is the plane generated by two non-collinear vectors. The plane generated by two non-collinear vectors. So if A and B are two non-collinear, the two vectors cannot be lying in the same line. Then you will not be able to generate a plane. They are two non-collinear vectors. Then there exists a unique plane, to A vector and B vector. This plane is known as the plane generated by A and B. By A and B, right? Okay, now how do we understand this better? So let AB be two non-collinear vectors. What we can say is that if R is any vector in the plane generated by A and B, then there exists a unique pair of real numbers x and y such that R vector will be equal to x times A vector plus y times B vector. So basically what I'm saying is that once you have a plane generated by two non-collinear vectors A and B, then any third vector in that plane can be written in terms of the linear combination of A and B. Any third vector can be written as x times A plus y times B vector. Okay, so let's think about this for a moment. So let's say we have a situation like this, where this is my point A and this is my origin. So this is my A vector and this is my point B. This is the origin. So this becomes your B vector, right? So what I want to show is that any other point, any point in this plane, this is the plane generated by A and B, right? Any point in this plane can be written as R vector. This is my R vector is equal to x times A plus y times B, right? For some real numbers x and y, right? So here we are saying A vector is OA, B vector is OB, right? And R vector is OP, right? So we can say that we can make a line parallel to B vector through P, line parallel to B vector through P, And we can also make a line parallel to A vector through P. And that will make us a parallelogram here, right? So basically, we can say that this point is L and B could be actually anywhere here. B could be somewhere here also. This point is M, right? This is M, this is L. How did I make this parallelogram? I, through the point P, which was given, I drew two lines, one line parallel to B vector and one line parallel to A vector. And obviously that makes it a parallelogram. So in this parallelogram, we can see that OL is equal to MP vector. And we can also see that OM is equal to LP vector because opposite sides are equal and parallel in a parallelogram, right? Now, since OA and OL are collinear, you can see clearly that OA and OL vector are collinear. We can write OL vector as x times OA vector, where x is a scalar, right? And similarly, OB and OM are collinear. So therefore, we can write OM as y times OB, right? Where y is also a scalar. And now we can easily say that the R vector is equal to OL plus OM because OL plus OM is the same as OL plus LP, right? And OL can be written as x times OA or x times A plus y times OM is y times OB, so y times B. So we are basically proving that any third vector in the same plane can be written as XA plus YB, right? Where X and Y are scalars. So that is the proof of the statement, right? So we are saying let A and B be any two non-collinear vectors if R is any vector such that R vector is equal to x times A plus y times B, where x and y are real numbers, where x and y are real numbers, then that means that R vector lies in the plane generated by, lies in the same plane as A vector and B vector. So this is also going to be important in the future when we discuss about coplanar points and so on. So right now understand that as long as you can write the third vector as a linear combination of your first two vectors, then the third vector is in the same plane as the first two, right? So basically now we can say that R, A, B are in the same plane and therefore they are called coplanar vectors. And the condition for coplanarity we are getting is that any one of them can be written as a linear combination of the other two, right? So I will restate that. Let A and B be two non-collinear vectors, non-collinear vectors. Then A, B, C are coplanar vectors if and only if C is equal to x times A plus y times B for some scalars x and y. So that is a very important condition to know. Okay. A generalization of this or a restatement, another way to say this is three vectors A, B, C are coplanar if and only if x times A plus y times B plus z times C is equal to 0 for some scalars x, y, and z, not all 0. Why am I saying that not all 0? Because if one of them also is non-zero, let's say z is non-zero, then that means z times c can be written as xa plus yb, and therefore c can be written as x by z a plus y by z b, right? And therefore we are getting these are real numbers. So we are able to say that C is a linear combination of A and B, and therefore ABC are coplanar by this property, right? If all three are 0, then you will not be able to write one of them in terms of the other two, right? So in that case, we cannot say that they are coplanar, right? Okay. Now we have understood when three vectors are coplanar, we have seen the condition for them being coplanar, where one vector can be written as the linear combination or in terms of the other two vectors, right? Multiplied by some scalar quantities. Now, the similar idea has been extended, and you can talk about now not three vectors, but 4 points. So let's say A, B, C, and D be the position vectors of 4 points, capital A, B, capital C, and capital D. And here, no 3 points are collinear. No 3 points here are collinear, right? Then we can say the 4 points, capital A, B, C, D, are coplanar, coplanar, if and only if we can write MA plus NB plus PC plus QD is equal to 0, where M, N, P, Q are scalars, not all 0. Not all 0, such that M plus N plus P plus Q is equal to 0, right? So this is an extension of the same coplanar idea, but now we are talking about 4 points rather than three vectors. You have to understand that if you have 4 points, then from those 4 points, you can make three vectors, right? So what I will do is I will do a proof of this. Pay attention to this proof. This is very important and you need to truly understand this. Otherwise, there will be problems for you. So suppose you have 4 points, A, B, C, D, which are coplanar, right? Now from the 4 points, we can make three vectors, right? AB vector, we can make AC vector, we can also make AD vector. So if the 4 points are coplanar, the three vectors are coplanar, right? These are obvious statements. Therefore, if the three vectors are coplanar, I should be able to write AD as x times AB plus y times AC, right? Here, x and y are some scalars. That is what we have learned about coplanar vectors, right? So now I can write AD. Think about it. AD is OD minus OA, where OD is the position vector of D and OA is the position vector of A. Similarly, this is OB minus OA, and this is OC minus OA, right? So I am able to write this as D minus A. Now I'm writing in terms of position vectors, not as AB, AC, AD vectors, right? So D minus A is X times B minus A plus Y times C minus A, right? And if you collect everything on one side, you will get 1 minus X minus Y times A plus X times B plus Y times C minus 1 times D is equal to 0. And now we can say that these are my M, N, P, and Q. So M is what? 1 minus X minus Y. N is what? X, Y is P, and Q is basically 1, minus 1. So you can clearly see that M plus N plus P plus Q is equal to 0. So if you are given 4 points and the position vectors of 4 points, what we are able to do is construct, and if the 4 points are coplanar, we are able to make 3 coplanar vectors out of them and use the condition for 3 vectors to be coplanar and basically prove our theorem. What was our theorem? That if 4 points A, B, C, D are there and their position vectors are A, B, C, D, these 4 points are coplanar if and only if you can write them as MA plus NB plus PC plus QD is 0 vector, where M plus N plus P plus Q is 0 and not all of them are 0. M and PQ are scalars, right? So this idea of coplanarity should be super clear to you. This is what we will use several times in problems. Okay. So I will stop at this point because we have covered a significant part of the theory. We have looked at collinear vectors and coplanar vectors, right? And basic properties of vectors also. We'll continue from this point in the next video. So stay tuned. You will learn everything that is required in this chapter. I plan to cover everything in detail. So if you pay attention to this series of videos, vectors and 3D should not be a problem for you. If you like the content, please subscribe to the channel and share it with your friends. And we'll continue in the next class. That's all for today.